Hello, everyone. Good morning or evening or whatever time it is where you are. Thanks for attending our Community Day and the final presentation in our Data Lake track. If you have any questions, you can submit them at any time through the question area on your screen. That's the little Q button on the bottom right. I'll relay them to the speakers when they're ready for questions. At this time, I'd like to give a warm welcome to our esteemed colleagues from North Carolina State University, who will be talking about their experiences building an agricultural data lake. First, Professor Kelly Zering from the Department of Agriculture. Kelly? Next, Professor Vince Freeh from the Computer Science Department. And last but not least, Computer Science Graduate Research Assistant, Gurman Singh. Take it away, Kelly.
Good afternoon, everybody, and welcome to our presentation. Thank you, Roger, for that fine introduction. We started this work several months ago, going on a year now, and I think we have something quite interesting to show you. So you might ask, what's our motivation? Why agriculture? And I'm an agricultural economist, so it's an area of particular interest to me. And during the presentation, I'll be giving you sort of a data customer's point of view on why we want this data accessible and why it's valuable. Agriculture is a huge industry worldwide. FAO estimates that it was worth $3.7 trillion in 2016, including about $327 billion in the US in that year. And that's just the farm level sales, not the value of the final products. Agriculture contributed about $132 billion to US gross domestic product. So that's the net value added by agriculture. And that was about 1/8 of the 1.05 trillion generated by agriculture, food, and related industries. So the difference between 327 billion and 132 billion is the value of inputs purchased from input suppliers and service suppliers to agriculture. And then everything above that is value added by processors and wholesalers and retailers and everything that has to happen in the supply chain after products leave the farm. Why agriculture? It's growing. It's not only huge, but it's growing. FAO and others predict 70% more food required by 2050 to feed 2 billion more people, about 30% more people on the planet. And those people and us will be generating 150% more GDP or more by that time, just extrapolating typical growth rates in GDP. So there's going to be tremendous demand for additional productivity from agriculture and related industries. Finally, why agriculture? Well, how big data is going to help feed 9 billion people by 2050 was a subject of a Tech Republic article in 2014. Business Wire last year did a study of agriculture analytics, just the analytics part of the market, and thought that would cross 2.5 billion by 2027. It's growing rapidly. So this is the early stage of a big data revolution. Why an agriculture data lake? And one problem is that there's a lot of data available in agriculture from USDA, from private markets that you'll see later in this presentation. But those data are currently scattered, they're difficult to access, and therefore costly to aggregate and analyze. Data include public and private inventories and ongoing streams. New data streams are high volume, high flow, and include new variables, reflecting new monitoring data logging and transmission capabilities that have come online over the last decade or so and are just in the early stages of adoption and utilization. And I'm going to turn this over to Vincent in a second. So who are the customers for an agriculture data lake? Anybody who's interested in businesses related to agriculture, analysts and decision makers across a vast array. Anybody who's interested in policy related to agriculture, food, energy, environment, ecology, broad swath of the economy that's impacted by agriculture. And finally, market analysts, investment managers, and risk managers across a broad spectrum are very interested in agriculture. With that, I'll turn it over to Vince. Thank you.
Thank you, Kelly. Thanks a lot. I really appreciate it. And I want to tell you, it's been a pleasure working with you over the last year. I've learned a lot. I'm fond of saying to my students, is I'm a computer science professor, and I say, I don't use computers. I just play with them. I just get to play with the computers and make them, go a little faster, or make them a little more capable. But Kelly's a real user. He has data and he has problems and he has really. So it's great when I can join up with somebody who has a problem, and then I can use these great techniques and great features that we have in our inventory to help them solve a problem. So one of the things what I'm going to do. Let me see. How come that? I'm trying to figure out how to advance this. Oh, there it is. Took me a second to learn this feature. I've been doing Zoom all my classes on Zoom, unfortunately. So I've just now figured out how to use Zoom, and now I'm learning how to use the Meridian software. So you're hopefully familiar with this slide, and I think you've seen it a few times already today. And it's a really nice way to depict the data lake, and that's where we're going to start. Is that we're talking about what we built with our system, which is a data lake. And so what I want to tell you is that we've broken our work into 4 layers. We're calling them layers, and we build those on top of each other. So each layer builds on top of the one below it. And so the first layer is what we're calling raw data. And that's just where we grab whatever, we grab the data and we store it. And this forms an archive. And so we can keep the data in that archive, which we can then use as ground truth. We can go back to it at any time and make sure that we looked at it correctly. And we can also go back to it and maybe interpret it a different way instead of just, and so it's really key that we keep everything we find, because we don't know what we're trying to do. I think if you watched Roger's talk, he said something about how it's important to have this because you don't really know the insights that you can get out of the data until you get further down the road. So we don't throw anything away. We throw that into the raw layer. But it's non-trivial to get that raw layer and have that nice and robust. So the second thing we do, the second layer, is we take that raw data and we transform it into what we're calling information. And so what we mean by that is that the data comes in raw and we have to convert it into types. Maybe some kind of a data. If it's a date, we have to tag it as a date, or it might be a value which it might be a dollar value which we want to put it in as a dollar. And then we also we do a little bit more in this layer where we create what we call derived data. So you might have a data set, and we have a data set from the USDA which has the amount of the crop that got planted, and also it has the amount that the crop that was also harvested in any particular season or year. And so what a derived piece of data might be that we say how much of the planted data was harvested. So we calculate the ratio of harvested over planted. And that can be an interesting thing to follow over time and see what happens. Maybe some years you don't harvest everything you plant for one reason or another. So that's an example of a derived data within a data set. But we also have derived data between data sets, because you can get some data from one source that has a lot of information, but it doesn't have the data coming in from another source. So an example of that is where we can get the yield information from the USDA, and we can get price information from somewhere else, and we can figure out whether or not there's a correlation between yield and price, or when price goes up, what happens to yield. And so we can ask questions like that. And those are just pieces of derived data, which we call information, and we put that in our information layer. We then build upon the information layer with what we call knowledge. And in this knowledge, what we do is we first of all do a lot of data mining to try to find some kind of an anomalies or some kind of a correlation between some variables, and then we can start asking questions. What's going on here? Why does this happen? And if we can see some patterns, or we can find some anomalies, we might be able to build some predictive analytics using AI or machine learning, and be able to build something even greater than just the raw information, a quantum leap more than just the data that's brought into us. And so then our last layer is where we deliver what we have. And so we have this data that we've had, and then we've turned it into information, then we turned it into knowledge, we've added knowledge. And now we want to do something with that, because just having the knowledge is great, but we want to do something with it. So the way that we would like to support the industry, the customers of our information, is to support decision making. And there's a lot of really important decisions that have to be made that we think we can allow people to make much better decisions, much more informed decisions, so that they'll be able to be more efficient and more targeted, and be able to not just make more money, but make more crop. And so this is one of the really important things that we, this is the cap of what we're building, and it's the most important part. If we can support decision making, we believe we can really have an effect on agriculture industry as we go down the road. So last, I want to say that in all of these cases, we use for every one of these layers, we use some part of the HPCC ecosystem. I've had the good fortune of being able to work with HPCC for several years on a couple of different projects, but this is the first project that has used so much of this much of the HPCC system. We use pretty much the full gamut, and we're not even using as much as we want to use. We're not using everything that's available in the HPCC ecosystem, and we're also not using each one of these things to the full extent that we plan to use them. But as we grow along, we're going to use a lot more of this system, and it's really been a pleasure to use this system, because it's highly integrated, it's very reliable, it's robust, it's fast, and once you get over the learning curve of ECL, then you don't want to do anything else, because it's just a really good way to access this data and to manage data at a large scale. So we're really happy to be using the HPCC system in this breadth. I mean, it's really nice to be able to do that. So we have a couple of goals that we want to do. Our primary goal is to build this public repository, and this public repository, we'd like to be able to, we want people to use it, look at it, and do their own research and their own data mining on it, and build tools with this repository. We're going to build our own tools, but we'd love it if some other people come up with other tools, because we don't know everything that needs to be done. And so that's the primary goal. Along with that, we have a whole bunch of other goals. We want to be able to make it easy to get the data there and scale the data and manage data. And we think that the HPCC systems platform is the exact one is the best one for handling our needs. And so we want to be able to support farmers and feed mills, which purchase a lot of crop. They'll purchase the crop in order to feed, in order to take some crop and feed maybe their chickens or their pigs. We have a lot of pigs in North Carolina, so it's important for them to be able to buy feed economically. Anyway, so what we want to do is build this data lake, and just reminding you a couple of the reasons why we chose a data lake is these are things we've probably heard earlier today, but it's really a good tool in order to support this kind of data. So before I turn this over to Gurman, I want to thank the people that have really helped us in this project. And the first one is our moderator, Roger Dev. He's joined our conference calls each week, and he's provided invaluable insights. And so we really appreciate the time that you have given us, Roger. Thank you very much for the time and your advice. And we'd also like to thank Dan Camper, who stood up a HPCC cluster for us to use, so that we have a managed cluster that we don't have to manage, and we get to take advantage of all the resources. Of course, I'd like to thank Flavio for his continued support of our efforts here at NC State. It's now going on probably about a half dozen years that he's been supporting us, and that we really appreciate that. And of course, nothing would happen without Trish, without the tireless work of Trish McCall. So we thank her for that. And so I'd like to invite Gurman to tell us what he's done. And by the way, Kelly and I have been working on this for more than a year, but Gurman just joined this in May, and he quickly picked up how to use the HPCC ecosystem, and then he's been able to really deliver a lot on that. So that's a good kudo to the training that we got at that's available at HPCC systems, and also the system itself. So Gurman, thank you very much for take over, please.
Thank you, Professor. Hello, everyone, and thank you for joining. So let's look at some of the initial phases of our data lake project. The first layer, as Professor Vince talked about, is the raw data, the data that we gather from a variety of sources, and that is still an ongoing process. We keep looking out for new data, new ideas related to agriculture, and then we try to figure out from where we can gather such type of data to work on. Now we'll look at the data sources that we have gathered and how we manage to process and extract information out of them. Here are two of the most important data sets that we have with us. One is the National Agricultural Statistics Services data, or as we call it, the NASS data. This is provided by the United States Department of Agriculture. The NASS data provides us with census and survey data of past 150 years. The other one is the Chicago Mercantile Exchange that runs the market for crop futures. Futures prices of various crops are available here, but we are only collecting the prices of three major crops right now, which are corn, wheat, and soybeans. Next up is the MASS data, or the Market Services data, again provided by the United States Department of Agriculture. The MASS data service gathers local market prices every day for various commodities from different feed mills and elevators across multiple states of the US. But we are only using North Carolina's market prices right now. And some of the other sources that we use to back our research are the Trade Adjusted Exchange Rate Indices from Federal Reserve Economic Data, hosted by the St. Louis Federal Bank, and the weather data from National Oceanic Atmospheric Administration. Now, collection of all of this data is not a one-time job. It is rather a continuous process. All of the data sources are updated periodically, if not daily. Access to latest data is very crucial for our work, especially when it comes to cases like prediction of crop prices. The upload of archival data is done manually only once. For the daily update of data, we wrote scripts in the backend that would make FTP or curl calls and upload the new data into the landing zone. The market prices from Mars is updated via curl commands, which make query for the new data daily and update the JSON responses in the landing zone. The NASS data is completely archival, so for the NASS update, the whole archive is updated periodically using FTP. Once the updates are complete in the landing zone, we spray the new data into the DFS using cron jobs written in ECL and in the HPCC server. Cron jobs are in sync with the backend scripts that we have. Now that we have our data in the cluster, we can start working on it, which includes pre-processing it and extracting as much information out of it as possible. First of all, we transform and add structure to the raw data, which is present in various formats like command separated values, comma separated values, tab separated values, JSON, or just plain text. We convert all these files into flat data sets. We also perform basic analysis of the data before flattening to assign correct data types to various fields of data, like dates, strings, or numeric values. This allows us to actually query and manipulate the data. We also perform certain validations as we will see in the following slides. During the process of flattening and transformation, we come across issues that are sometimes unexpected and unprecedented. For example, we noticed that CME data have their dates stored in two different formats. You don't expect a table to have two different formats of date in the same data set. Right when we were in the phase of inducting the MASS data into our lake, they changed their data delivery format from document style delivery to an API format that provides JSON objects as data. Most recently, we noticed that ECL parses dates like the given here as 2068, whereas actually it was 1968. This here is an example of the NASS dataset entries and the corresponding record structure. As you can see, the dataset consists of multiple columns for representing the same data. I mean, we have still not found an entry where these columns have different values, and there are more columns like these. Also, because the structure that data is in, these columns become redundant sometimes. Like when data is at the state level, these county columns entries are 0. Now we will look deeper into the various data and their properties, starting with the largest of all, the NASS data. The NASS data contains census and survey data of everything related to agriculture, be it data for individual crops like area harvested or crop yields, and that too divided based on different utilization practices or production practices. It has data corresponding to different geographical levels from county to national level, dating back to the mid-19th century. It also has other non-crop related data like economics, animal produce, environmental, and demographic data. We receive the NASS data in the form of 5 files corresponding to the 5 different sectors that I just mentioned. And that is all of the logical separation of data that NASS did for us. The combined size of the data sums up to more than 45 million entries. The base structure of the dataset consists of 38 columns, as we just saw over here. Every row gives us a single value represented by 37 attributes associated with it. These attributes can be divided into 3 main categories: the what part for what data is being represented, the where part for where it was recorded, and the when part for when it was recorded. The main challenge with the NASS dataset is that even though it covers a large variety of agriculture data, such as crop yield or area planted, all these various types of data are aggregated together using the same set of 37 attributes, which makes it a very difficult task to identify and extract different types of agriculture data from this dataset. During our initial analysis, when we grouped together 10 attributes corresponding to the what part of the dataset, we learned that there are almost 58,000 metrics of data that we can work with, but it is all mixed together using in a single table using the same attributes. On top of that, more than 50,000 of such metrics do not have even 100 data points. But this is not the end of challenges yet. The biggest challenge that we have to face is that in this dataset is its inconsistency. For example, here is one of the tasks that we were working on. The plan was to extract the data points like area planted and yield with respect to irrigated and non-irrigated fields and analyze the effects of irrigation on crop. We expected to see results matching the general idea that irrigation improves crop yield. But as it turned out, only 7 states had enough data for such an analysis. And when we look deeper into that data, we find inconsistent values like here, where only 1 year had irrigated, 1 year for one county, we only have 14 acres of irrigated crops, land that was irrigated, compared to the 100 acres of non-irrigated. And even that did not sum up to the 114 to say. So as a result, we ended up dropping the whole idea because of the inconsistent data. So this is kind of our normal routine where we come up with some hypotheses, some turn out to be true, and some we are not even able to test. Coming back to the topic of data transformation. Coming back to the topic of data transformation and extraction, here we have the CME Futures contract. Futures contract is data is important because it provides best available estimate of future prices of a crop. The interesting part in the processing of this data is that we had to extract information from the names of the source file as well. The CME data comes in the form of hundreds of files where each file corresponds to the timeline of a single contract. Along with the task of managing multiple files and grouping their data together into a flat data sets, we also need to extract contract level information from the name of the files. This information includes the type of crop and the contract expiration date. To achieve this, we assemble all the files into a superfile and use normalization and transformation features of the ECL to extract information from the file names. Here is the example of the mass archive data that we had to format. Currently, the data comes in JSON format, which is much easier to pass, but the mass service did not change the format for the archival data, so we had to pass these documents to collect the archival data as well. Another issue that we face here is the discontinuity in the data. These are the data availability plots for different grain elevator and feed mills over the time. As you can see, almost none of these data is continuous, which causes a great challenge for analyzing trends and other machine learning tasks. Once we have the logical and simplified datasets with us, we can better look into the data from an agricultural perspective. We now know what types of data we want to look into, and that might give us insights regarding valuable knowledge and important crop trends. For that, we created this web application in Flutter framework for better access to the data. Now, I'll share my screen before talking further. So this is the application. And here we can enter whatever states we want to look at the data for, and we can collect the data at annual level or monthly level stats, or we can even get the county level data. Once we have this with us, we select the crop, which crop we want to look up the data for. And so this data that we transformed with us, we deployed that into the Roxy server of HPCC cluster, which was exposed via web services. So this application accesses that data using REST calls. So that data comes in here, and we can see the yield trends for all of the counties of NC state over here. And we can click on any one of these to expand. So as you can see, these are the yield values over the time for Wake County. If we choose, we can compare this with other counties as well. Let's say we choose Henderson. And here we can compare the analysis or stats of the two counties together. As you can see, this is a county level data for one county. We can also choose to see the data for the whole state, like here. So this is the same yield stats for NC state timeline, but these are for wheat. And as Professor talked about earlier, we also have some derived data. These are the trends for area harvested over the planted. And again, we can also choose to compare this data with other states like Arizona. And again, we find that, okay, the Arizona yield has been better than North Carolina's over the past years. And me being a computer science person, it makes more sense for an agricultural expert like Professor Zering. So he might have a few more additional comments over this. He might have additional insights on this. Professor, do you have some comments right now?
Yes, thank you, Gurman. I'll just add a few comments here. So what you're seeing seems fairly straightforward, and yet when you compare it to the form and type of data that's normally available to users around the world, you might get a table with 1 year's yield for a few locations, or maybe 3 years yield for a few locations. But to retrieve the data for hundreds of counties, for all 50 states, for 20 years or 50 years or 150 years, then you've got some real work to do. And here, after Gurman and Vince's work, I can retrieve this data in a matter of seconds. And all sorts of insights emerge from this. You can use this data in trend analysis and prediction. You can use this data to decompose national yield trends and to compose forecasts for the country by aggregating predictions in different states. You have 4 headings up there that you can look at. Area harvested tells you how many acres each state or county produces compared to the rest of the country. Production, which gives you a total amount produced by that state or county in a particular year. Yield, which you've been looking at, and then a derived ratio of area harvested to area planted. So a tremendous amount of data is at your fingertips in just a small screen here, and that's immensely valuable. This is the stuff that goes into daily decision making, strategic decision making, policy making, you name it. So I just want to give you that perspective on the value that's represented here. Thank you, Gurman.
Yeah, thank you, Professor. So this is the kind that since Professor Zering is able to tell us that, okay, this thing would be valuable for the agricultural field. So I will now, since Professor Vincent here, I'll hand over it back to him. Thank you, Professor.
Thank you, Gurman. And so I just want to reiterate a little bit about, or just point out something that is very important about what we just witnessed. The data that we have is multifaceted, and I can only really think in 3 dimensions. So I think of like a cube, and so there's many ways you can look at it. You can choose a slice one way and look at the data in that way, or you can choose to slice it another way, and you can choose it to slice. But the insights about how we needed to look at this data are not something that I was able to really understand. And so it took a lot of a lot of discussion with Kelly to figure out what is it that we want to know, what are the pieces of information that we like to know. And so it's a mechanical thing for Gurman to build a filter that allows us to filter by county or filter by, but it takes a little bit of insight to figure out what's the important thing, what is the nugget of information that you want to extract. And so this has been really so the thing that Gurman's created is pretty, I think it's pretty impressive. He's been able to build this up, and again, he just started in May, so he was able to build this also over the summer and get this thing set up, including learning a whole bunch of stuff about ECL and Flutter, and then all about the data set. And so that's a testament not just to Gurman, but to the robustness of ECL. I don't think it's, and probably to Kelly's ability to explain things. I don't know how much I got credit for that, but what I would like to do is talk about what we now do in what I call the knowledge layer. And so first of all, knowledge is the knowledge layer we build off of information. And an important part of what we get in the information is derived data, because the data, the raw data isn't necessarily exactly what we want to see. It has a lot of the information, but it doesn't necessarily have the nugget that is going to make that we really need to look at in order to do our analysis. So an example of that is that if you look at the grain market information, which comes from the Chicago Mercantile Exchange, so that's a market where we sell contracts, and so there's people who buy and sell these contracts for up to 2 years before the contract expires. And so we have the data. We know how the market moves, so we see the open and close price for every day, and we can track this thing over time. And so that's a great piece of information to have. But what in order to do our analysis, we need to add a few pieces of information. One of the things that was really important was to add the closing to the days until closing. So when you look at a lot of this data, what you'll see that the contract expires on a particular date, and and the date changes every year. So it's not so important what was the price at, say, August 1st, but rather what was the price 25 days before every price expires. So we added things like the price, the cost of the days remaining in the contract. We also wanted to know when it was trading on that day in August and it's going to sell in September. Wanted to know, was it above or below the final closing price? So we added all these things to each row, and then we were able to do more information, be able to do more direct analysis of the data. So this is what we meant by derived data, and this is something we do in an ECL script, and we do it right on in the data set. We throw it into our tables that we create, into the files that we create. Another example, which we've talked about quite a bit, was harvested over planted ratio, and that's a really important thing. The next thing that we found that's really important is something called a basis calculation, which I'm going to invite Kelly to explain.
Thank you, Vince. So basis is a fundamental concept in Sorry, I'm just fiddling with controls here. Just trying to share my camera so you can see my face. But yeah, so basis is a fundamental thing in economics, and particularly in marketing of crops and other commodities. And basis is very simply the difference between the cash price at some location on some date and the futures market price for the same commodity with a given expiration date and location implied. So this is, and why this is important is because if you try to hedge using just the futures market, you've left a portion of the price that you'll actually receive or have to pay unhedged. And that's that difference between the cash price and the futures price. We could look at the next slide maybe, but this is a depiction of cleaned data. So the spikes have been removed where there was missing data or bad data. You still see a few outliers there. You see a pretty prolific trend over the course of 20 years. This is North Carolina. I believe these are corn prices. And this is a very significant difference between what North Carolina people receive and pay for corn in North Carolina versus what the futures market is offering on any given day. So I think this is a September contract in particular. But anyway, we're getting a very dramatic trend over time. Good news if you're selling corn, not so good news if you're buying corn. But important to know the trends in order to be able to predict what might happen in the coming year. The following slide shows us a few more subtleties and important characteristics of these data. So we've compared, actually on Roger's advice, we've compared an additive type basis, the difference between cash and the nearby futures, versus relative or proportional relationship between cash and the nearby futures. And you see slightly different patterns, although the trends, underlying trends are still evident there. So this is again that 20-year time series, and you see the upward trends, and you see some volatility in the short run and in longer run cycles. And so we haven't had the opportunity to explore those yet, but though correlating those to outside events will help us make a better prediction for the near term. Over on the right here, you see a slightly different presentation. So these data are gathered by time of year. So there's 366 days represented here. And I think all 20 contracts, all 20 years for September. And you see an annual pattern emerge in the basis. And we've set September as the zero date, and then the end of August the following year as the ending date. So what you see happening here is that grain is harvested and the basis is very low. There's a surplus of grain available relative to the world market at that point. And then as local supplies get consumed and imported supplies are required, you see the basis slipping up and up and up. And then it drops pretty dramatically back down again in September. So this annual pattern gives us a lot of opportunity for hedging or planning purchases and storage. Some people refer to this as the storage premium in basis. There's also a storage premium in the futures market. So again, to step back, there's a huge amount of data represented here, and it's been transformed and presented in a way that's really useful and informative to people interested in grain markets. And it is the basis for making predictions and for making really sound fiscal decisions and managing risk in this very risky industry. And Roger, I'll turn it back to you. Or sorry, Vince. I'm sorry, Vince. I'll turn it back to you.
That's okay. I wish I got confused with Roger more often. So what I'm now gonna talk to you about is a couple of pieces of analysis that we're doing in which are the beginnings of our machine learning or predictive analytics work. And so first I'm going to present this futures data. So this again is September corn contract. We've focused most of our information. We've chosen to present mostly September corn, although there's lots of choices beyond just the September contracts and the corn as a crop. What I'm plotting here is over 70 years worth of corn contracts. And so this is the relative price that the contract is trading at on a day-to-day basis. On the x-axis, what we have the days remaining in the contract. So on the right-hand side, it's 0. So that's when the contract expires. And on the left-hand side, it's a little bit over 600. So almost 2 years before the contract expires. So there's trading that goes on as much as 2 years before the contract expires. But although most of the trading, we'll see on the later slide, is concentrated in the last 90 days of the contract. But you can look at this and you can see that the contracts vary wildly. Some of them are as low as $3. The y-axis is the number of cents. Contracts are traded in cents, and so the number of pennies that we are deviated from what the final contract is. So you can see that this green line here towards the bottom, that one that's trading at about $3 less than what it finally trades at, and this one up here trades at about $4.50 more than the contract resolved at. And so you can see some people were able to make money at this, and a lot of people and some people lost money on this kind of stuff. And if you just notice the trend here, you'll see that it seems like the market is pretty optimistic as the average is always above 0 in this case, more than that. So the average is always above 0, and so that's interesting. One of the things I want to do is just look at this red contract, which starts out here, and you can see it jumps around, and even here, just 90 days away from the contract, it's it's almost $3 below the trending price, the final closing price, and then it actually creeps up in here. You can't quite see it because it's hidden, and before it trades off. And so that's a particularly interesting contract. And so we wanted to see what happened during that contract. So I'm now zooming in on just that one. And so I'm showing 3 plots here. And so this is the corn crop for September of 1973. So that was back a few years. I don't know how many of you people remember what it was like back then, but this was how the contract traded. And if you can see, well, the top graph shows the value of the contract over time. So this is you see the pennies, and so it says, it started out at $2.50 here at about a year out, and then it trades, and it finally gets up to $3.50, and then drops down to about $2.45 is what it finally sold at. This green line represents the opening price, and the red line represents when it's the final closing price of this. And you can see how the price stayed fairly consistent for the first half, until about 6 months before the contract. And then for some reason it grew very high, and it grew to way above what it finally ended up trading at. So there's a lot of volatility. This was a very unusual plot. Normally they don't bounce around this big. So this is one of the reasons why we chose to look at it. The middle graph, the middle chart there shows the volume that's being traded. So this is the daily volume that's traded in blue. And so you can see some spikes in that as it goes up and down quite a bit over the day. And this is very unusual. Most of the contracts have a fairly steady volume. They traded a certain volume, and the next day is about the same amount of volume as trade. It starts out really slow at the beginning. Not many people are interested in hedging in betting on the crop prices a year out. But a lot of people start to bet on it as we get closer into the close of the contract. But this one's unusual because it's volatility. It's up and down. There's a lot of trading one day and then much less the next day, and so it's really high. And so that was unusual. We thought that found that curious. Oh, by the way, the red line on this, the red line here is the cumulative volume. So if you take all the volumes that happen every day, and you add them together, you get this cumulative volume. So this is the total amount that was actually contracts traded and so on. And this bottom one is the outstanding, it's the open interest. It shows the outstanding contracts. And so this is typical of most contracts, in that there's not many contracts in the beginning, and then at some point they start to go up, and the contracts start to go up, and then they peak, and people then start cashing in the last 90 days, last 60 days of the contract to try to make their monies before the end of it. So anyway, we found this very interesting. We looked at this. So we went back into the history books to find out what was going on in September of 2000, in September of or what was going on in 73. Why we would see such a strange contract. And so it turns out that the Arab oil embargo started in October of 1973. And so I think there were a lot of nervous investors in the summer preceding there, because I'm sure that the oil embargo didn't just appear overnight. There were some events leading up to it, some conflicts among the world. So you can see from this contract that there was a lot of nervousness in the market, and people were using the market probably to try to manage risk of other investments as well. Because I'm sure if we plotted the oil contracts during that time period, it'd be even more volatile than this. Anyway, this is just an example of some of the insight that we're able to create just by grabbing this data out of the contract. So speaking of open interest, what we've talking about here is this right here is the open interest. That's how many contracts are currently traded. So I mean, somebody's bought a contract and it hasn't been sold, or somebody has a contract that has sold a contract that nobody's bought yet. And so here's a plot of open interest over time, and I'm going to ask Kelly to tell you why this is a very interesting plot.
Thank you, Vince. So there are 5 contracts represented here. I'm going to be very brief because I see we're down to just a few minutes remaining, and I know Vince has something important to show you. But what this shows is that somewhere in the mid-90s, there was tremendous interest in futures markets, especially for corn. And so there were a lot of open contracts. People poured a lot of money into these contracts, and there's a buyer and a seller for every contract that's open at the time. And then interest died way down, and it's been gradually recovering since then. So this provides additional explanatory information as we go about trying to predict things.
Thanks, Kelly. And as a reminder, and realizing that we're running out of time, I'm gonna do a little bit of a briefer discussion of this. But what we're talking about here, what I'm showing here is local prices. Now, these are not the future contracts. This is the prices that are actually delivered to when a farmer delivers grain to some location. And so this is the price that he's given, or if somebody's consuming the price, this is how much they pay for that crop. And so what we've plotted is we're plotting corn here, and what we're plotting is dollars per bushel on the y-axis, and then 20 years worth of time across the x-axis. And there's 13 time series there for 13 different elevators or feed mills that are accepting contract. And we were surprised in a way, but not surprised at how closely these prices correlated. And so we did some analysis. We said, are these things truly correlated? And so there's this thing called Granger causality. When I was practicing this, my kid thought I was talking about Hermione Granger because they're all into Harry Potter again. But this is a different Granger, I believe. And what Granger causality says, the question we asked was, is there a time series here, one of these time series that can predict the other time series? And we found that Statesville, which is somewhere in the center of our state, seems to predict all the other prices very well. So we did a linear regression on this analysis and found that they had really good values for mean squared error and R squared. And so we believe that it was highly predictable. So we can predict. So if we have the Statesville price, we can predict with high accuracy the price that tomorrow. So we have Statesville price today. We can predict tomorrow's price at the other 12 feed mills. And so you can see that what we realize here is there's a slight difference. And so, for example, Candor is about a little over 2% more than Statesville throughout the year, throughout all these predictions. But something like Cresswell is about 3% less than Statesville. So this was a very useful thing to know. And I'm sort of surprised at how tightly they're correlated, because these feed mills are geographically displaced, and it's not easy for a farmer to sell to anybody but the closest feed mill. So I would think that they would have less, they would not be as lockstep, but it turns out that they are highly correlated, and I guess that's good news in a lot of ways for farmers. So here's what we really wanted to do. What we wanted to do was predict what the farmer could expect for his crop. He's going to have to pick what to plant, and he has to then say, what am I going to get? And so what we wanted to do was find out what could the farmer get for his crop 6 months down the road. So we figure that the futures market is the best predictor of what the future price is going to be, because we have these individuals who are betting their own money on what the price is. They're using everything they have to bet this, and they're willing to put skin in the game. And so these are reasonable choices. And we can see that the price here, this is 180 days before. This is the price of 180 days before the contract is due. And you can see that it's pretty much normally distributed around a mean of 1, except it's not quite a mean of 1. It actually is a mean of 4.5% higher than 1. So the market seems to be a little optimistic, trading at about 5% higher than what it's going to eventually sell at. But it's normally distributed about across that thing. And so we'd like to be able to predict that. I'm going to kind of skip through the next step, which is where I was going to tell you how we did some prediction. I'm just going to go and tell you that we weren't very fortunate in our prediction, because we've learned that prediction is pretty hard, especially about the future. But what I'm going to do instead is I'm going to share my screen and make sure that I can figure out how this works. And so this is an example of a tool that we built for predicting crop mix. And so the idea is that a farmer has to decide what he's going to do with his crop before when he plants, and we want to assist him in managing risk. So kind of quickly here, we'll go through a few examples. What we have here is we have an example. The very first example I'll say is that we have an unlimited budget. So that's so that we can spend as much money as we want. And so now if we look at 3 different crops, what I plot here is profit versus risk. But before I do that, let me show you what we're looking at. And so we find out that the price that you can expect to get for we find a distribution for the price that you might be able to expect from a crop. So let's look into wheat. And so we figure out that the gross revenue for wheat is a function of the gross revenue, which is dollars per acre, is equal to the expected price in dollars per bushel times the expected yield, which is bushels per acre, and that's what you're going to get your gross revenue. Well, we can predict the price based on previous data and the yield based on previous data. We can then put those two distributions together, and we can come up with a gross distribution. And then we have an expected value, how much it costs you per acre to plant that crop. And so now what we can do is we can then assess a risk there. And so we can look now here, we have 3 crops, and there's 66 different ways in which you can plant 3 crops over 10 fields. And here's an example of these different distributions. And so what we now look at is this is the expected value that you're going to get here. This y-axis is the average of the net profit that you're going to get for your crop. And then the risk, what we've chosen to use to represent risk, is the first hex tile, which means 1/6 of the time you're going to make this money or less, or 5/6 of the time you're going to make this money or more. And so that's our risk. And so it gives you a chance to assess profit and risk. And generally, profit and risk flow in this direction. The higher profit has higher risk, which is more negative value, and then the lower profit tends to have lower risk. And so this is an example of what might happen with these 3 crops. And so we can also look at another scenario where we look at all the crops. And in here we have over 10,000 different possible scenarios that could possibly happen, because we're allowing up to 7 different crops in here. And since we have an unlimited budget, what we end up planting mostly is a lot of sweet potatoes, because sweet potatoes, while they cost a whole bunch, like almost 36, they cost 10 times as much per acre as wheat. plant and harvest, but you can make about you can make thousands of dollars per acre. But of course, you might lose thousands of dollars per acre. So what we plant here, what we show here is all the plots, and then the size of this dot is how much it costs to plant that. And so this is interesting because it's all crops. Let me go quickly back here, and this is the last thing I'll show you. Is I'll show you if you have a farm budget. In this case, we have a budget that only allows us to spend $750,000, not an infinite amount. And you can see that when we look at all the crops, we have far fewer possible choices because we can't afford to plant 1,000 acres of sweet corn, of sweet potatoes. So we end up having to plant a whole bunch of other things. Anyway, this gives the farmer a chance to look in here and say, well, what's the deal with this particular scenario? And this scenario costs us a little over $500,000. We have this distribution of plants, and here's what our net profit's going to be. We have a chance of making almost double our 50% of our investment, but we could lose it all. And so that's lose half of it. And so that's this tool that we're trying to create. And so that's all I'm going to show now, since we'd like to leave room for questions. But I'll let Kelly have the last word on telling you why decision support tools are the most important thing, or are such an important thing to create.
Thank you, Vince. I think in a few words, data is like ore. It's valuable, but not that valuable. It's what you refine from it. Information is more valuable, and knowledge is valuable. But if you don't really have a use for it, it's sort of an arcane interest or a scholarly thing. But ultimately, the value of data comes in how it can improve decisions to do just about anything. And whether that's in the market, whether it's in how to decide what to grow and how to grow it in agriculture, or how to operate other businesses related to agriculture, how to manage risk in all of those businesses. So what's really impressive to me about this project is we've integrated a lot of data in a very short period of time. We've made it accessible, and we've just scratched the surface in terms of data that's available in agriculture today. There's so much more to do. But the fact that we're able to offer extraordinary decision support already for people in the markets means a lot. So thank you for this opportunity. Roger, do we have time for a question?
Yeah, thank you, gentlemen. That was outstanding. Very, very good work. We do have one question, and I'm going to ask it, and then I'm going to dart off to my next presentation. So I will let you guys answer that. So the question is, this tool does an excellent job of showing the economic trends over time and planning for the financial aspects of agriculture. Could this tool and data also help with planning demand as our population grows to ensure we are producing enough to sustain our growth? Or is there a separate set of data required to make that determination? And with that, I'll leave you guys to answer.
Thank you, Roger. Kelly, would you like to take a first stab at that?
I would like to take a first stab at that. That's sort of an economics question. It can be used to address the question of how much food is needed in the future and at what price. So another set of data would help us with population demographics. And another set of data tells us about how people consume food and agricultural products, basically the demand as a function of their GDP or income. And so we would integrate the production data with the population and demand data and come up with forecasts. And that's what the FAO has done in some fashion when they say there will be a demand for 70% more food in 30 years. And that's what many other leaders are doing in terms of anticipating where markets are going, where international trade is going, and generally speaking, where the welfare of people in different parts of the world is going. So maybe that's a bit more than you wanted to hear, but yes, this data is essential in being able to predict how much we can produce and what the value of research in agriculture and innovations that are just now emerging and innovations in the future, what the value of those innovations will be. So unlimited applications and value to be derived here. Vince?
Well, I think we're out of time, but thank you, Kelly. I really appreciate that. So we've really enjoyed this, and I believe we're just going to get cut off. I just got told we were out of time. So thank you all. Thank you for attending. And I don't have our contact information here, but you can find it if you'd like to talk more. Thank you.